Welcome to the continuation of my ADTA 5560 project. And so going from part 2 to 3, looking at the sine wave data. This is the report. We're gonna go through my report. I'm gonna go with more of a walkthrough method, more like lecture style. And so the next part is part 3, looking at the long short-term memory neural network and kind of the core concepts in here. So you look at the core concepts, we have the cell state and the gates, and you gotta actually, describe the two core concepts and what they are. So with the cell C state being considered as the information transporting channel, it transfers information from the earliest time steps all the way to the end in like a sequencing chain. This is what amazing picture of a cell state kind of looks like, and this is a cell state and the gates and function together. So we'll get a picture, a screenshot of that. And so that is basically what the cell C state is. It's more of a transporting channel. In theory, basically it carries relevant information through the process of a sequence. So as we go to understand the gates and how the gates work with the cell C state and how it flows through together. So we have the gates. First, looking at the forget gate, which decides what information from the cell state that should be removed or irrelevant as it passes through this channel flow. And so what information should be kept or removed. And so relevant or insignificant information is determined through this gate, and this gate does most of that work in the training process. And the output of the forget gate tells the cell which information should forget by multiplying by 0 in a position matrix. So you look at basically the positions that they have in that state in the LSTM neural network. And then go ahead and look at the input gate, which decides what information from the inputs is also useful and should be added or saved to the new cell state. As an important part of this input gate is usually where you have your activation function, which is either a TANH, ReLU, any activation function, but you see the TANH here. So you're just looking at basically the basic LSTM cell. You do have the input gate right here. You have your output. And the output gate computes and extracts the new current cell state at the time, at whatever time it is in, and decides what information from the inputs and the new current cell state should be used to make the hidden state at that time, at that particular time. And so look at the three gates of the LSTM network. You have your forget gate, input gate, and the output gate, how they all work in the LSTM network in conjunction with the cell state to be functional, to create a model, any model that's going to be trained in the LSTM neural network. So the cell state, looking at some of the differences and the similarities, is cell state, which is a memory in the LSTM cell, and the hidden state, which is actually the cell output. And so this is the difference you have there, and the similarities. Hidden state is the output of the STM cell, which is used for prediction. It contains the previous information, the information from previous outputs from that cell state, along with current input, to decide, in context, which is important. And so this is a small part of the project, middle section, just kind of talking about this. And so going from looking at simple RNN on sine wave data, we taking the step into Jupyter Notebook next to look at the time series data, which I chose the daily minimum temperatures of Melbourne, Australia, from a time period of 1981 to 1984. And we're going to train two models there, actually create one model and to redesign the model just to see which model looks better. So using the LSTM neural network instead of simple RNN. And so that's what we'll be doing next. So here, I'm looking at the time series data on my time series model on my data set. So yeah, in Jupyter Notebook, we're gonna import the libraries that I needed to carry this out. And in the beginning of my project, in the first video, you saw the import what I did to put the daily minimum temperatures. I put the date and the end date in there for the daily minimum temperatures in Australia, putting in the virtual instance for that to be loaded into my Jupyter Notebook and being able to perform, different brief EDAs here on the data set and then going ahead and plotting this and then finally creating the data set. And so we're going to walk through that just a little bit here. So, just basically looking at the small ED on the data set. So I have two columns and 1,382 rows of being the observations. And so a little summary statistics here with this code. And then it's finally giving me a plot. So this is a basic time series plot on the daily minimum temperatures, which you expect some seasonality. This is a chart, a time series chart that does show seasonality. And this, you would expect that being that it is a daily minimum temperatures, as it goes high and low, basically on different dates and times in different years, you expect it to be seasonal, temperature being seasonal in that based on country. And so explain and train the city set my test percentage. I went with 10% for the testing, the part of the data used for testing, 10% off the data. And so here normalizing the data, which is scaling into a range to make this building and testing the model efficient. So here, building and training the model, the most important thing is going with the standard inputs here. I chose 50 neurons, and I'm going to go back over that as we go through the final report. But 50 neurons for this one to train this model that I chose. I'm going to use 50 neurons, and so basically run this to 100 epochs. Takes a little bit of time, and so here you see a loss plot of what the loss looks like. See a significant drop, and it kind of stalls out here. And so you predict future data points with testing, which is, after we create the model, you want to test the model. You're going to test the model against the actual, so separate data set that you're not using. So the training is done on that 10% of the data. So doing the training on the 10% of the data, we get the prediction. So the prediction is this. So now with this prediction here, pretty much going to compare that on the test data. And so if we hear in that prediction, this is what I kind of got, it's not too bad, with what to expect here. It still falls in line. It could be closer in the thickness of this seasonality, how far they go down. But so this was my first model. This is just standard model on the data set, the minimum daily temperatures in Melbourne, Australia. So the next part of this, I'm gonna be showing you the redesign model and kind of my thought process and what parameters to change, what core parameters needed to be changed for me to try to improve the model, to get any improvement, if any. And so I'll be looking at that. So looking at my redesign model here, we're gonna look at what I chose to do here to improve my model. So I went with deciding to change the number of neurons to train that I use to train my model, my prediction model, because I tried a few things, try to increase the percentage of the dropout, but this model generator here, the epochs, I mean, it's just a difficult thing to deal with. Took some time, take some time. And so I daisy decided to not mess with that and mainly focus on the neurons. I just believe just with the thought process, the fact that, just increasing the number of neurons, which means just increasing the number of kind of computational power, used on my model. And so, with the 100 neurons, got the loss function, like always, creating a time series generator, you get the prediction. And so you look at this prediction and how it fits on the actual. And now we can see the the denseness, the tightness in the lines, and it being closer. So just comparing the two briefly, because I'm actually going to compare the two as I do the walkthrough to the report. This was the original one, the first time series model that I created, and this is the second one. So you can see I did a little bit of improvement in my eyes. The way I decided to look at it is it could, if I maybe increase the numbers to 200, if a third redesign was needed, that was the only thing I was thinking about changing here. And so with that being said, these are the two models that I have, and going to compare the models and kind of taking you through the core parameters. I'll be doing a walkthrough through my actual Word document, since I'm going with the walkthrough approach. Start with a presentation today. So looking through the first part 4, which is the design of the long short-term memory neural network, it's kind of basic design that I had, and so summarizing the core parameters, percentage of data chosen for testing, like you saw in my Jupyter notebook, at 10%. How many LSTM layers? I had 3 over them. And then the number of neurons in each LSTM layer, 50 neurons, a couple of dropout layers, and I used 20% for the dropout there. And length of the time series input sequence was 60, and the batch size for training was 1. Like, and the number of epochs was 100. So basically, looking at a report that I had, building and training the LSTM network to perform forecasting using TensorFlow backend and Keras. Basically, it was done on the daily temperature city of Melbourne, Australia, where there's a records in temperature degrees Celsius. So those data records were in degrees Celsius. See a screenshot of the normalized prediction. And so the normalized prediction, we run the actual prediction, got the values, and then we visualize that. And so, as I showed before, the visualization of the data for the first one, was here as seen a much thinner line. And then you look at the prediction compared to the actual minimum daily temperatures chart. And so that was there. But before of the redesign was, I didn't really have any structural differences in the architecture of the neural network. I wasn't adding any more layers. I didn't add any dropout layer, any new LSTM layer. I still went with a standard 3 LSTM layers to dropout layers. And so what I did was basically change some of the core parameters. And the most important thing I did change was the number of neurons. So most of them stayed the same. And 1 batch and 100 epochs. And so there you see the code where I changed the number of neurons to 100 from 50. And actually what that did, like I said, for me, the logic behind that was increasing the neurons. To me, just meant increasing how much, model training was done. It's just drilling down more. So I think with 200, I would have got closer. And so with that being done, this was the visualization that I had. And so comparing the network performances against each other, so comparing the two science models, the only true change was increasing the number of neurons, as that was the only variable to have any effective change. Model 2 was more redesigned with the 100 neurons. So I put them side by side here, and obviously you can see the difference, and I like the visual as it does show the difference here, and how close the second one is to the actual versus this in terms of just the look in the chart. Just look. And so gonna just walk you through the project report. Introduction to the report, building, training, testing the simple RNN models and LSTM models on various data sets. Report to the project, I actually find a data set that was a time series data set, you know, which was not something we had done in class. So finding the time series data set. So we're just going over my time series data set as I'm walking through my project. You guys do my project report. There's a time series data set for minimum daily temperatures data set of recorded minimum daily temperatures in the city of Melbourne, Australia, during the span of 4 years from January 1st, 1981 to October 13th, 1984, 383 observations in this data set, and the data set was accredited to the Australian Bureau of Meteorology. So, and then I actually got the download from a different website, which is machinelearningmastery.com. And so, with that being the case, that was the first part of the project from my project report. And part 3 was creating the sine wave data like we saw. I created the sine wave data by setting the parameters of the sine wave data and the proportion in the portion of Jupyter Notebook, and was able to build a model to predict the sine wave data and compare the predictions to the actual. And so that went down. And in part 3 of the project, you know, going over some of the core concepts of LSTM cells, which is the cell state and the gates for get input and output, like I did go through how they function in the network and the functions of each core component. Also looking at some similarities and differences. And so part 4 of the project, using the LSTM to create a time series model on my daily temperatures data set, and was able to build the model, train the model successfully, working through the code, working through the notebook, making sure the code was right, making sure my parameters were right. And so that was the first part of the LSTM portion with building the time series data. And part 5, an attempt to improve the model, whether I did get one or not. Luckily, I did get one. I think I just affected the right variable to change, which is the number of neurons. So in part 4, an attempt to improve the model, I chose to increase the number of neurons used to train the model, and this slightly improved my model. As I saw the chart with seasonality, the redesigned prediction model looked closely similar to the actual. So this is a seasonality chart, not straight up like a stock chart. A stock price will go up and down slowly over time. This just goes on daily, with daily and being seasonal. You see daily through months and years, how that is going to be. And so have a chart looking like that. And so in conclusion, during this project, the deeper understanding for me was just understanding how simple recurrent neural networks worked, how they're structured, how they're built, and possible ways to improve models, just changing different parameters of your model and being able to affect it on different types of data set that fit the time series model. This model can be used on it to improve it, to get predictions. And also same thing with the simple recurrent neural network for sine wave data. So this is my ADTA 5560 final project, and it's Kwame Darko Mensah, and this is the end of my presentation. Thank you.